Hello. So my name is Kyle. I'm the dev rel at Fhenix, and let's just dive right in. It's 20 minutes, so I'll try to make it quick, go through this. I'm going to go over like FHE, how to build private applications on an ETHRome using Solidity. So let's just go into it. If anyone's interested in working on Fhenix, here's a quick link to join the Discord. I'll take it here in case someone needs it. Here's also a cheat sheet if anyone's interested in kind of just getting set up, configuring your application. It's relatively quick. Okay, so I'll just dive right into the presentation from here. So what is FHE? I'm not sure if you guys are familiar, how familiar you guys with the concept of like fully homomorphic encryption. But it's basically the ability to do operations over ciphertext or just do operations on a hash, usually in general encryption or general privacy. Since you can't really do these operations, apply logic to like encrypted fields, what you end up doing is decrypting. So if you don't take anything else away from this talk, just think that fully homomorphic encryption is the ability to do operations over an encrypted field without decrypting. So homomorphic encryption is kind of like when you are able to, let's say you want to add two numbers, two encrypted numbers, like 5 + 5 is 10, but you don't want to actually leak what either of these numbers are or what the output is. So basically you're able to run this on an encrypted value, two encrypted values. So communication here is client-side only, where you're basically generating the ciphertext, encrypting it locally, and then passing it into what is essentially the server in this case, which is the blockchain. Okay, so let's just dive into more high-level stuff here. So I'm sure a lot of you guys are familiar with the concept of using like zero-knowledge proofs for privacy, and we'll kind of go into like why there's issues with that and where fully homomorphic encryption can help this. But from a high level, basically, homomorphic encryption is something that's existed, since the seminal works released in the 70s. In 2009, this guy Craig Gentry came up with this concept of bootstrapping, and FHE uses this noisy encryption, which is basically kind of using fake stuff to obfuscate the truth, kind of like when you're playing poker. You don't want to necessarily just play each hand straight up, or the one time you go in, people know you have nuts. But either way, there's been a lot of evolution from this like bootstrapping breakthrough, which was kind of the ability to have constant size noise. So you can essentially checkpoint it so it doesn't cascade and compound exponentially and then prevent decryption. I won't spend too much time going over this, but basically there's two main branches kind of right now when you think of the applicational FHE. There's something called like a leveled schemes approach, like it's just CKKS, which is, good for things like, theoretically good for things like machine learning. You have approximate math, you have float, and it won't necessarily bootstrap under each operation. You have something like fast bootstrapping, like TFHE, for example, which is what we're currently using at Fhenix, but we're open to integrating into different schemes. But this is good for Boolean circuits if you want to actually compare two bits and get a deterministic value from that. So kind of like what I was just saying, sort of here is sort of the high-level overview of kind of like different, more popular, kind of going in the order of these different FHE schemes, and there's pros and cons of each. Again, I won't spend too much time on this, but if you have any questions, feel free to come to me in the booth or just I'll be around. So I'm just bringing this up mostly just because like in the Ethereum Web3 zeitgeist, whatever you want to call it, people like kind of conflate ZK with privacy. So there are kind of some issues with this. Basically, if you have adversarial inputs that you don't want to link to the prover, if you have adversarial inputs that you want to verify, how are you necessarily going to be able to prevent this from leaking to the prover? For example, if like I have information about something in private state, someone else has another information about a private state, how do you necessarily address this? Usually this involves some sort of reveal scheme. Applications lack flexibility. I think a lot of times people think of something like ZKP and they're like, wow, like I should be able to check that I'm 18 without revealing that I'm 18 or something, but then we should be able to theoretically scale that to more like branching, compounding logic, but it's mostly just, I guess, kind of like, lipstick on a pig to some degree. So in this regard, if you're doing this, the plain text does become known. So this can kind of work for like some single party use cases, but it's difficult if you want to have a shared state, which is kind of one of the reasons why I think some people prefer to use FHE for ZK, for privacy versus ZK. And again, like what really is necessarily ZK? I mean, I think when people tend to conflate something like a ZK snark, but like I guess this is syncness and the compression, all these things really kind of come from the underlying proof system, and ZK is kind of just a way to prevent an input, prevent the input from leaking, keep your inputs private, classic stuff. Anyways, here's kind of a quick overview of different PETs. I won't spend too much time on it, but like something like TE has expressiveness as well, although there's always going to be known attack vectors that are kind of known. MPC theoretically gives you this private Turing completeness with different type of like additive secret sharing that can be used in conjunction with other methods. But again, this is always going to be communication about how does it scale when you have multiple parties if you have more, I guess, complex states that need to be managed. And you guys might be more familiar with this concept that's coming up like co-snarks and stuff. But under the hood, what's that basically doing? I mean, some would say it has the latency issues of MPC with the proof overhead generation issues of ZK. So we've already kind of talked about like the issues with ZK for specifically privacy, and then FHE is kind of one of those things where it's like, hey, minimal communication because it's non-interactive. We'll go into that a little bit more in detail. But the computation is slow. There's hardware acceleration. You know, you have like that are trying to perform like different faster operations, and this is becoming more apparent with the rise of ASICs in like 2025, and you have governmental entities really investing heavily into FHE hardware acceleration, just because I guess the lattice-based schemes are going to prevent like some underground quantum computing lab from basically just these large prime factorizations or whatever, because it's lattice-based, right? So it's a fundamentally different encryption hard problem that's difficult to solve. But anyways, not to get too much into this, but sometimes we were like, why not use something like TE? I guess it's kind of different. It's like you trying to go for like pure cryptographic security. You're just trying to use it for something that's like, okay, we have like this secure enclave that we can do whatever we want, and maybe there's like manufacturing use, side channels attacks, etc. But homomorphic encryption, again, when I try to think of it like homomorphic encryption versus MPC, which I think is arguably maybe the most closest comparison, and we'll get into how at Phenix we use these in conjunction. But the issue here is really the interactive versus non-interactive nature of it, because if you have a non-interactive protocol, you can essentially scale it up. Gives you a lot more flexibility of what you can and can't do. Versus MPC is always going to have these known communications, like latency. What do you do if a node goes off, etc. What do you do if you have too many parties and you can go to everybody? So from a high level, here's sort of like this diagram kind of like what you can do with MPC versus FHE. Just if I don't know, maybe you guys that are a little bit more visual, you kind of see how these like nodes or whatever, kind of each of these users kind of have to need to communicate to like verify and run operations on this shared state, if you would, versus like just kind of like sending them to the server. The server in this case is like the blockchain VM. So it's just one of those things where it's like, I think this is arguably maybe a closer comparison to something like people tend to conflate again, like ZK with privacy. But like, when you think about like, what do you want to do if you want to have like arbitrary computation on like a shared state, like this is kind of what it comes down to. So it really kind of comes down to interactive versus non-interactive. Anyways, so like how does the FHE rollup work? If you could think about it from a high level, basically, it's not too different from a normal, like I guess standard EVM L2. We'll go into the details about how this works a little bit, but the decryption is kind of handled by this threshold network. And the FHEOS is basically what kind of allows us to run these operations as general expressions on top of like whatever blockchain you want to work on, interact with the threshold network. But again, we'll get a little bit more into that detail. Like I said, we're interested in adding like different types of schemes. Specifically, if you need something that has like, if you know something has a fixed amount of like operations, it's ephemeral. Maybe it's an inference for like a machine learning thing. Maybe it's a certain voter set. You don't necessarily need to use like a Boolean circuit scheme. You could use something that has like, a leveled scheme. But anyway, so the threshold network. So some of you might be like, how is this safe? So like theoretically, the secret key, the server key, which all these ciphertexts are supposed to be encrypted under, are split and distributed between different nodes. So this is kind of used for decryptions, re-encryptions. Re-encryptions we'll get to a little bit later, but it's basically like how do you view this data? It's sort of like stateless decrypt, and you wrap it with a specific user's public key, give that sealed output, and then the client, only the client will be able to actually like kind of unwrap it for the application. But again, we'll get into that later. This is going to be bound by the standard MPC trust assumptions, like how do you handle the ciphertext reconstructions, etc. So this is where a lot of research is currently being done. And fraud proof. So again, we're like an L2, so somehow you have to settle back to the L1, right? It's basic stuff. So right now we're using a fraud proof instead of like something maybe more familiar like a ZKVM, buzzword, whatever that's called, like a Validium, just for the, so yeah, it does sacrifice the sync verification, the constant time verification, instant settlement, whatever you want to call it. But from a high level, you can kind of think of it, I like to think something like, for those of you who might be familiar with this concept of like Arbitrum stylus, which kind of has these two VMs for like the Solidity EVM, and then like through it, you have like this interface that like can interact with like the WASM VM. And we're running these FHE operations in Rust just because like it's not really feasible to do in Solidity. So you like basically call these precompiles. These precompiles will do whatever necessary operation. Proof of these operations, the call from the EVM, are basically going to be settled to the L1. So it works like a standard L2 in that sense. So FHE coprocessor, it's a weird thing. This L2 fragmented liquidity. People are like, goddamn, another fucking L2. So it's like, okay, why don't we just try to like go to the consumers where they are, right? Like if people want to use FHE, why make them come to our chain? Why don't we go to them? So like the concept of coprocessor, this should be able to be run on an L1. Theoretically, it could be run on like other VMs, like I guess an SVM in the future, like base, scroll, whatever you want to call it. So it worked pretty similar to how I was describing earlier, where you have this like segregated relay, and basically if you call a specific function, it's going to pick up the event, and then it's going to run the computation and verify it, post the verification onto the L1. High level, that was a lot of word garbage for basically saying that like we are currently working to add FHE to like your favorite, EVM, L1, L2, whatever. So here's kind of the high level review. If I had more time, I'd love to go more into it. If you have any questions, find me, I'll be around. Okay, so real quickly, let's just go over kind of how you would build a Fhenix. I think it's actually pretty feasible to build in the scope of a hackathon in a couple days because we're not expecting you to learn a new language. It's, EVM compatible, basic Solidity. So like, as you can see on line 4 here, you're basically just importing the code from our contracts. And you kind of have these numbers, etc. So TLDR, you don't have to learn a new language. You can just use Solidity, your favorite shit that you normally do when you do like Web3 building, whatever. So not reinventing the wheel here. For those of you that are interested in local setup using hard hat, we have a doc. So these are kind of just examples of how you can work on Fhenix if you're interested. There's also a Remix plugin, so you can use Remix to kind of generate these ciphertext and do the sealed outputs. I think this is kind of nice if you're a visual learner. Maybe it's your first time. Maybe it's popping your cherry with FHE. It's just like, might be a good way to kind of dip your toes in the pool. And then there's currently Foundry support with mock operations. I mean, I think Foundry is just becoming more popular as a developer environment in general. So these are the ways that your options working with Fhenix. So real quickly, let's kind of just go into the inputs. So this whole thing, what the fuck was I even saying this whole time? Basically, for those of you that are familiar with Solidity, there's a concept of like an unsigned integer, different arbitrary bit lengths. So like U256, uint256, but let's just take a uint8, for example, represents any number from 0 to 255, sorry. So basically, these are ways that you can, you think of this encrypted number, right? Like instead of just adding 5 and 5 and then getting this 10, it's like encrypted value, EUINT is kind of what it sounds like. It's an encrypted unsigned integer of bit length, arbitrary bit length. In this case, it's bit length 8. And so you add those two numbers and it gets the sum of these numbers, and each of it will be private. So these are kind of the ways that you can pass them into your function parameters, basically. So we have this data type called inEUINT8, which is basically what it sounds like, and then you assign it to an EUINT value, and from there you can do things that you would normally do in a Solidity contract: add numbers, use it as value in a key mapping, etc. Standard stuff with numbers. For those who prefer to just raw dog the bytecode, you can also just send an arbitrary bytecode bytes if that's simpler for you. Maybe a user application, I think maybe it's not as intuitive, but again, there's always that option. So the other thing that's a little bit tricky is that there's this branching doesn't necessarily work in FHE, because just in the sense that it's kind of like constant time code. So, I'm sure we're all familiar with like, first week of like intro coding classes, like if else, but it doesn't really work. So you have to use the selector method, which is kind of like here, which basically you pass an encrypted Boolean, which is basically as A is less than B. And then if it is, you assign it to A, or if it's not, you assign it to B. So an encrypted Boolean is what it sounds like. It's an encrypted value. It's either 0 or 1. So from there, I like to think of it that like FHE doesn't have conditional write, but it has conditional assignment. So if you have conditional assignment, you can kind of handle your branching logic that way. Require statements basically work like how you would expect a normal require statement in like Solidity to work, except now you're just checking like a ciphertext relative to another ciphertext or a value. So it's kind of a decrypt under the hood, so it's going to be held to the same MPC performance requirements, etc. Another thing to consider is conversion leakage. What we want to avoid here is leaking plain text to memory. Generally speaking, this is like where a lot of vulnerabilities happen, whether it's on server, etc. So again, in FHE, the nice thing here is we don't have to ever decrypt, because we can always do these operations on encrypted values, so it doesn't leak. So here's just kind of a quick little like tip, right? Like you can't pass in a plain text number, encrypt it, and then just be like, all right, this shit's fucking safe. Because like it's gonna leak. It's blockchain, right? The whole stack trace is basically available. Every single state change down the road, every single thing that happened is gonna be there. So it's extremely vulnerable. So this is something not to do. Because basically, if there was a plain text ever in the history of it, it's gonna leak. So Phenix.js is basically the JavaScript library that you can use to interact with Fhenix. So this is like kind of the other part of it. Personally, I don't think it's like too tricky. There's really like two things you need to do here. So for those of you who are familiar with working with a standard API integration, using something like ETHRome.js, where you basically, hey, this is my contract, this is my function, this is what I need to pass into my function. Before, it used to be like, hey, let's just pass in an unsigned integer of like 8-bit length, and this is the number 5. Now you basically just take it as like, okay, hey, let's encrypt the number 5. This new object is what we're going to pass into our function. Not too different. So permissions again are kind of just like who has certain access to view something, like a certain encrypted field, right? Like if I have a FHE private OnlyFans and I want to make sure that only people that are paying for my nudes are able to see my, my nudes or whatever. Like this is basically how you can make it conditional. So like I said earlier, this is basically kind of like a decrypt under the hood, a stateless decrypt, where you re-encrypt a sealed output. So you're taking this value, the plain text value, after the threshold, whatever network has decided that like, okay, it's valid for this person to view this. You get that, you wrap it with a specific user's public key, and that's the object that you return. Once the object is called from the application to the client can then verify through their signature in their browser. So this is basically a way that you can kind of do like access control version, or access control. Yes, it's basically a modifier. We're just checking to make sure that the correct message.sender has the correct pub key access. So again, here you can kind of do it in the client. And again, there's like conditional logic that you can sign up. Like, hey, only the premium fans can see like this month's, I don't know, nude pic or whatever. So again, yeah, that was pretty much the presentation. I just want to reiterate like a few things, like, FHE allows you to do operations without decrypting. You don't necessarily have to, learn a new language. It's all Solidity native. Unlike ZK, you can handle kind of this shared private state. So it kind of allows you to do, I don't know, I guess a lot of things that we actually want to do on blockchain, like a cool actual DeFi, not just like private execution, which kind of is just like a time lock or like some sort of reveal scheme anyway. There's no necessarily need to have these like off-chain like keys, whatever. And unlike MPC, it's not going to be communication bound. Unlike T's, you're not going to have like the physical limitation attack vectors. So general runtime tips if you run into block overflows or anything, or if you try to build a Fhenix. So just try to remember that the operations that you do are going to make a difference. For example, dividing two numbers are going to, all things held equal, are going to be more, it's going to be more computationally expensive than adding two numbers. And also the bit length is going to make a difference, such as like adding to 8-bit numbers is going to be cheaper than like adding to 256s, right? Pretty intuitive. And again, you might think that like ChatGPT maybe it might be so straightforward, but we actually have like a custom ChatGPT for Fhenix that you guys can use. That's trying to train on our docs and some contracts, so it's not bad. So anyways, if you guys are interested in filling out this survey for us, it would help help us figure out what you're interested, how we can best help you, things you're looking for, common questions, or if you just want to get in contact with us. But yeah, that was the presentation. I appreciate you guys taking the time to listen to me ramble. So if you have any questions, I'd be happy to answer anything. Other than that, I'll be around. So. Good.